got a motorcycle accelerating up a ramp here, like this. Oh wait, gotta have these so you know he's actually driving. All right. So now he's accelerating up the ramp. We're trying to find the acceleration. We have a bunch of forces acting on him. All right. So we've got it's red because he's communist. We have mg acting downward. What else we have? Okay, we have normal force. What else we have? We have kinetic friction. I don't know if we're going to have friction in this one. I think since it's rolling, we're going to sort of discount any friction aspect. We have force up the ramp. Do we know what the force up the ramp is? All right, we have a known force up the ramp, capital F. What else do we have acting on it? They give it just sort of as in general terms. It gives a air resistance, a resistive force, right? We'll just give R there, okay? So now, we're given the force, we're given F, and we're given R. How come what's difficult about this? Not difficult, or, why do they bother giving this problem? This is X and Y. We're rotating our coordinate axis system. Okay? What do we have? What else do we have acting on it? Well, that's all we have acting on it, but we need to figure out what's acting in the X direction, right? Going back to our Mach 51 or 52 or whatever it was, we were able to look at a free body diagram and determine the forces that are acting in any given direction. So we're looking for the forces that are acting in what we're calling now our X direction. That is parallel to the ramp, right? Because we know he's not going to sink into the ramp. He's not going to bounce up off the ramp. We're hoping, right? So the net force in our new Y direction is 0. And the force in our XY direction, we're going to determine the net force so that we can determine what his acceleration is going to be, right? All right, so let's take a look. Net force acting, we're just going to call it X. Net force acting in the X direction is equal to MAX. True because? It's always true. Net force acting in the X direction is equal to, now let's think. This is where we have to get a little bit clever here. We have to pay attention to detail. What's acting in the positive direction? F, right? The applied force that we know, his driving force. That is friction, by the way. Whoever mentioned friction, who had mentioned friction? Oh, okay. But there is friction because that's actually the force that's driving him up the ramp. Okay? But we'll just call it F because it's given as such. All right? Anything else acting in the positive X direction? Nothing else acting in the positive X direction, right? Anything acting in the negative X direction? R and? Yes. We have mg parallel, or we'll put it in next, and that's going to be mg sine theta. That is correct in this case, which is easy because the sine of 30 is 0.5. Okay? So, I'm assuming that it gives us his mass as well, or his weight. What's it give us? That's the whole motorcycle and rider together?
I guess so.
Okay. All right, so let's just two-equation strategy this thing, and we'll go MAX is equal to F minus the quantity R plus mg parallel, or mg sine theta. Okay? I just distributed the negative sign there. So that means that the acceleration is going to be equal to this quantity given up here, F minus the quantity R plus mg sine theta, both of those acting down, all divided by m, the mass of the motorcycle and motorcycle rider as a system. All right, so now we get A, and force is equal to, in newtons? 3150 newtons, okay? Minus the quantity, what is that air resistance it's given? Louder, please. 250 newtons plus mg. What's 290? You told me before. What's 292 kilograms times g. Oh, looks like we're gonna have to make all this smaller. Group 292 kilograms times 9.8 meters per second squared times the sine of 30, 0.5. You guys okay with me just doing that straight off? Not worrying about putting it in there. All right, and then all divided by, oh, the mass, 292 kilograms. All right, so that's just a number crunching problem, and I'll pause while we do that. All right, number crunching gives us 5.03 meters per second squared. I'll look it back. I'm going to assume that we have 3 sig figs everywhere because that's the way the purple book gives it, and they're pretty diligent about sig figs. So 5.03 meters per second squared, that's fast. That's a pretty significant acceleration. All right, now, you might want to challenge yourself and see what would happen if you turned the motorcycle around with exactly the same forces acting. What would be his acceleration down the hill? You expect it to be greater or less? Greater, sure you would, because in this case, if just as a quick extension, if you had the motorcycle going down the hill, and then so this F acting downward, it would change R probably, because the faster you go, the greater air resistance is, but no big deal. All right, and in this case, we'd have a component of mg acting with us, so our net force would be bigger, wouldn't it? Okay, so we would accelerate at a greater rate.